In this lecture, I will discuss the lasso. The lasso is one particular form of penalized regression, where the penalty that we add is in terms of the L1 norm, or the sum of the absolute values of the coefficients. So we try to find a balance between fit, the first term measures the lack of fit in a least square sense, and the penalty, which penalizes if we include too much in our beta, if our beta is too large. So if you write that as a constraint minimization problem, then we saw that this constraint here, because of the absolute value, has these sharp non-differentiable points, which means that we both shrink towards zero and do variable selection. So this is the same graph as in the previous lecture, where we see that we can end up exactly on the axis where beta 2 is equal to 0 because of these non-differentiable points. Yet on the other hand, we have convexity, so in terms of optimization, this can be pretty fast. Before I go into how the method works, let me first mention a short note about standardization. So if we want to have our lasso work properly, we should make sure to standardize the predictors, or at least to carefully think about beforehand whether we should standardize predictors. Now this is something when you do least squares you don't particularly care about that because it doesn't matter, but here it actually does. What we'll see is that some estimates may get unfairly penalized. So take a model like this. I have two regressors, x1 and x2, beta 1 and beta 2. And I think that you could transform x2 by multiplying it by c. So we create x2 star multiplied by c. Obviously the model would stay the same, it's just that beta 2 star would be beta 2 divided by c. Again, if we do these squares, we don't care, we just get this multiplication factor gets absorbed in the coefficient we find. But things are different here because suppose that we multiply with a very small number, so we scale it down. That means that beta 2 star will get blown up because here we divide beta 2 by c. And that means that actually you would get a much larger penalty on beta 2 star, whereas it does not actually change your fit. So this creates a very strange situation where you don't change the fit, but you do change the penalty by multiplication here. Now we can see that again, if we look at the two components, the residual sum of squares remains the same as before, but the penalty does not remain the same. Right? In the new model, you actually get a different penalty. So your objective function, if I go back here, the objective value of the objective function will be different. So the only thing we did was scale these columns, but it has an impact on the objective function. It also means, of course, that the optimum might not be located in the same place anymore. So you can get very strange artifacts here of how you scale. So what we normally do is we just standardize, right? We make sure that all the axes have mean 0 and variance 1 to make sure they all get treated equally. Normally you also would not want to penalize an intercept, given that gets strange situations if suddenly you don't have an intercept included anymore. So the easiest way to do that in practice is actually you standardize y2 because that eliminates the intercept, and then you can run the Lasso regression without intercept. For instance, standard packages in R, such as glmnet, which is the standard package for Lasso, does this, all of these standardization steps automatically. Okay, so let's now look at actually how do we compute the Lasso and why does it do variable selection? Well, first thing to note is, of course, if we have a convex objective function, we know that every minimum is a global minimum. That's, of course, the advantage of convexity and why it matters so much for optimization purposes. So you don't have to go search over local minimum. which means that you only have to consider the first order derivatives and set them equal to 0. Now, the lasso, of course, it doesn't work for that because we have a non-differentiability. The absolute value creates a problem with differentiability. So that also means that we cannot do what we did for Ridge. We cannot get an analytical solution directly. So that will not help us. Now, we can actually characterize the solution, and we can show some important properties of the Lasso solution, but for that we need to slightly expand our machinery for convex optimization. So what we're going to define is something called the subgradient. And the subgradient is a line, essentially, any vector z that satisfies this inequality. Right, so you take a point x and you have a line z such that essentially moving away in a linear way from that point x, you remain below the function value at the new point x star. So we're approximating in a way this function with it linearly, and we should remain below the function values. Now, as you will see, if the function is differentiable, there's only one such set, and that's of course formed by the derivatives. But if we have convexity but non-differentiability, there can be multiple ones. And this collection of all of these sets is called the subdifferential, and we denote that with this symbol. So let's look at the situation where p is 1, right? So we're just looking at the real line, which is a bit easier than in higher dimensions. So the subgradient now in real line is just this function, satisfying this inequality here. Right, and here you can really see that this is a straight line, so it's a linear approximation. We base it on tangency at the point fx, and we want this line to stay below the function values at x star, and it should hold at all x star. So of course you can rewrite this, right? If you want to solve for z, we can rewrite this, and of course what we can simply do, well, we get fx to the other side, and then we divide by x star minus x. Of course here we should be careful, because if x star minus x is negative, the sign of the inequality will flip. So we treat the two cases separately. For x star larger than x, the sign doesn't flip, and we get that z should satisfy this inequality. And for x star smaller than x, the sign does flip, and we get this inequality. Now you can already see that actually what we have here, if we take the limit of x star going to x, it's a definition of the derivative. And that simply means that if f is differentiable at the point x, then this can only hold for the derivative. So the subdifferential that we're now defining actually reduces to just standard differentiability if the function is differentiable. Now let's take the function that we are interested in, the absolute value. So fx is absolute value of x. Well, we also know that if x is not 0, well then of course the function is just differentiable, right? There's no problem at any point apart from 0. So we consider x is equal to 0. Right, then we're going to solve for these two equations. Well, what is this fx star minus fx divided by x star minus x? Well, x is 0, so this x becomes 0, so in the denominator we just get x star. In the numerator, we get absolute value of x star minus 0. So this expression reduces to the absolute value of x star divided by x star, which, if we think about it, is just equal to the sign of x star. Right? It's going to be 1 if x star is positive, because then the absolute value is equal to the number. It's going to be minus 1 if x star is negative, because then here we get something positive and here we get the same thing negative. So this just being 1 for positive x star and minus 1 for negative x star, it just reduces to the collection of lines for z being smaller equal than 1 for positive, z being larger equal to minus 1 for negative. So if z is in between these things, it's satisfied. So the collection of all subgradients is the set -1 to 1. Now this is easiest to actually illustrate graphically. So the solid blue line here is the absolute value, right? So we plot the absolute value of x. So we have x on the horizontal axis and the absolute value here. At point 0, we have the non-differentiability. And here you see several subgradients drawn. So these are all straight lines which are tangent here to the function at 0 and which all remain below the function value. And their slopes are equal to z. So this one has a slope of -0.6. We have, of course, one which is equal to 0, and this one is 0.9. And you can see that you can go up to 1, and here you can go up to -1, which is exactly what we found analytically. Now, the nice thing about the subdifferential is that it allows us to also extend finding minima, where for a differentiable convex function, we know it has a global minimum if the derivative at that point is equal to 0. For subdifferentials, we extend that by saying it's a global minimum if 0 is included in the subdifferential. Again, if the function is differentiable, this is just reduced to the standard condition. But we actually want now to extend that to deal with the absolute value function. So we can characterize the solution of the Lasso by saying the subdifferential should include 0. So if the point beta at the point beta where the solution is. Well, the first part of the subdifferential related to the least squares part is just the derivative. Of course, the problem is only happening here, and only actually when beta or elements of beta equal to 0. And only those partial derivatives are problematic, they don't exist. So let's keep it here for now, to keep the subdifferential of this function here. And now let's look at specific elements. Right, so take the jth element, so the jth component here. Take the derivative with respect to the jth component. Well, if that component is not 0, then the partial derivative with respect to beta j is just the sign again, right? It's either 1 or -1. If it's equal to 0, the derivative doesn't exist, and we need to take the subdifferential -1 up to 1 into account. Now, what does that mean for the first order conditions? Well, take the jth first order condition, so the derivative or subgradient with respect to the jth component. Well, so that means we need to take here the jth row of these things. So let x dot j indicate the jth column of x. And then we can take out that row from this whole vector by taking out the jth column of x, and it's then doing it transposed. So this would be the jth row, and we would get just the sign 1 or -1 here. Well, if you write it out, you get this expression, which looks actually not too bad, and looks like something we might be able to solve. Now the problem, of course, is that actually here this beta factor, or in this double sum, depends on all entries of the beta, so not just only on a single one, which makes it hard to solve this. And of course, we have assumed here that actually our beta j is not equal to 0. So what happens to rows where beta j is equal to 0? Well, there we define a new variable, say uj, which should be between -1 and 1, so there's a 1 missing here. And then we can say, with that variable, which represents the subdifferential, there must be some value in between -1 and 1, which makes this equation be 0. So if we put the two together, we define now an sj, and we say this variable sj is the sign of the beta j if it's non-zero, and it's some element between -1 and 1 if it is 0. So this is the first order condition of the Lasso, the jth first order condition. We can write that, of course, for every j1 up to p. Unfortunately, this is as far as we get, and we cannot solve this analytically any further. Now, as you will see when we look at how we actually compute the lasso, this will actually be the basis of computations. But we still want to go a bit further and express the solution in a nicer way. So what we're going to do is we're going to assume orthogonality. Orthogonality, as we already seen in earlier lectures, means that x prime x over n is equal to the identity matrix. In that case, life simplifies because now the jth row of x prime x times beta over n is just beta j. So we have a massive simplification here. We here only end up with beta j and not with all of the betas. Right, so all of the entries in the sum except for beta j will be 0. And then suddenly, of course, things become a lot easier to solve. So this will now become the first order condition. Well, let's start by solving it in a way where beta j will be equal to this quantity here. Of course, we haven't actually solved it yet because the value of sj depends on the value of beta j. So we still have beta j on the left and beta j on the right, even though we didn't write it explicitly here. But we can now look at the different cases. So take a beta j larger than 0. Then we know that sj is 1. Right, so in that case, we could plug 1 in here. Now, could this be a solution? Well, it can be a solution if this expression with 1 plugged in is larger than 0. Because then we have a match, right? We said beta j larger than 0 here, and beta j is indeed larger than 0 here. So if this is the case, if this is larger than 0, this could be a solution. Now, why would that be the case? Well, of course, if the first part here is larger than the second part, so the xj prime y over n should be larger than lambda over 2. But we can do, of course, exactly the same for the negative solution. Beta j is smaller than 0. We plug in sj is minus 1, and we check if actually now the expression here is negative. Of course, because we have a minus 1 here, times minus becomes a plus. And so we need that this quantity here to be smaller than 0. That means that x prime y over n should be smaller than minus lambda over 2 for this to be a solution. So already note that you don't have to worry that you could end up with both being a solution, which would be problematic, which would contradict convexity. Because of course, only one of these conditions can happen. That is either, it cannot be both larger than something positive and smaller than something negative. Of course, there's still a gap in between, and as you can probably already guess, the gap will be the case where we need to look at beta j equal to 0. So let's do that next. So take beta j equal to 0. Well, in that case, going back one slide, the left-hand side here will just be 0, right? We say beta j equal to 0. This sj thing can now be somewhere in between minus 1 and 1. But with this equal to 0, we also know that this part here, the first part, xj prime y over n, should be equal to lambda sj over 2. So that's exactly what we have here. We need that x prime y over n is equal to sj or lambda over 2, but sj does not have one value, it can have any value between minus 1 and 1. So we need this to be true for some value between minus 1 and 1. Well, the largest value this can take is of course lambda over 2. The smallest value it can take is minus lambda over 2. And if sj is 1, you get lambda over 2, sj is minus 1, you get minus lambda over 2, which means that xj prime y over n should be in between lambda over 2 and minus lambda over 2. So if this is the case, then beta j equal to 0 is a solution. So if we put all the three cases together, if x prime j times y over n is large enough, we would get a positive solution, and the solution has this form, right? This is exactly the first order condition. If xj prime y over n is negative enough, so minus lambda over 2, we get this solution, which is going to be a negative solution. If xj prime y over n is close to 0, at least close enough, closer than lambda over 2, then we decide to take beta j equal to 0. So we see that in this case, actually, the variable selection is happening. Now, let's link this back to least squares. Right, we know the least squares estimator, but we assumed orthogonality. So orthogonality means that actually this inverse of x prime x reduces to the identity matrix divided by n. So our least squares estimator under orthogonality looks like this. And then we see actually what we had in the previous slide, that this can now be seen as the jth row of the least squares estimator, or the least squares estimator for element j. So we can replace that by beta hat OLS for element j. And so we can see this in a way as a sort of a two-step procedure where we would first calculate the least squares estimator. And if this is large enough, if we're convinced it's far enough away from 0, where far enough depends on lambda, we keep beta j, our solution, positive, although we do subtract something, so we move it a bit closer to 0. Right? We reduce it by lambda over 2. On the other hand, if beta hat OLS j is negative enough, we keep the negative solution, but again, we add a bit to move it a bit closer to 0. And if it's not far enough away from 0, if it's an absolute value smaller than lambda over 2, we just say it's 0. So this is what we are doing, is sort of thresholding, and we call this the soft thresholding estimator. The soft part comes from the fact that we don't just threshold, right? So this is the thresholding step, but also when we don't threshold, we still move it towards 0, so we shrink towards 0. We can also write that in this form, so you can see if you write out the cases that actually this form is equal to that form. So we do both shrinkage and selection. And we can easily illustrate that graphically. So we have the least squares estimator on the horizontal axis and the lasso on the vertical axis. Now, of course, the 45-degree line just represents the least squares estimator, right? Or setting lambda equal to 0. So there the estimators will be equal. Now, what does the lasso do? Well, if you are within lambda over 2 from the origin, you set the estimator equal to 0. Once you move away from that, you move in parallel to the least squares, but you reduce it with lambda over 2 to move it closer to 0. So here we see the variable selection, and here we see the shrinkage. That explains how the lasso works and why it works. Of course, what we still need to do is analyze what theoretical consequences does this have. But before we do that, let's move a bit to this parameter lambda, because this of course plays a crucial role. When we go back to the graph, if you make lambda very large, right, so you put it here somewhere, that means you will put the lasso coefficients very likely equal to 0. Plus you additionally increase the shrinkage, so it will also induce much more bias. On the other hand, if you don't do it, right, you could say, okay, well, we don't want lambda to be large, well, let's put it equal to 0, you're back in the least squares case. Of course, that has all the problems with overfitting and high variance in high dimensions. So we have to find an appropriate trade-off there. Now we can give theoretical arguments, which will be part of one of the follow-up lectures. Let's here look at how we do it in practice. So we have to find some way to say, get a lambda which on the one hand doesn't put too many coefficients to 0, doesn't do too much selection because it will kill off relevant variables and induce a large bias. But on the other hand, it should be large enough that we actually can handle the high dimensionality. And now thankfully, we can go back to our model selection world where we already looked at information criteria and cross-validation. But doing it directly on the least squares problem, that was unfeasible, but doing it on the lasso is feasible. So we're not doing it directly, but we're doing it on lambda. So how do we do it in practice? Well, cross-validation, we need to define a grid, say lambda 1 up to lambda g. Well, there are many ways to build a grid, but the sort of standard is to build a grid which is on the log scale has the same distances. So we can use these formulas over here. They don't matter too much. Let me focus just on this first one here, the largest value of lambda g. So the largest value that we take is equal to this quantity, and this comes directly from the first order conditions. And we know that if all of these inner products are smaller or equal than lambda, everything will be set to 0. So we don't need to make lambda larger than these inner products, the maximum overall coefficients of these or variables for these inner products. So once we have our grid, well, we just do the k-fold cross-validation, and you can use 5-fold or 10-fold depending on what you want. And we look at, for instance, the squared prediction error and find that lambda out of that grid, which minimizes that prediction error. And now the nice thing is that when you have to evaluate this for cross-validation, you only have to evaluate it g times. And typically this would be, say, 50 values or maybe 100 values, which is much less than the 2 to the power p models you would have to evaluate if you would evaluate all possible models. And that is, looking just at 50 is actually enough to find out a value which is close enough to the optimum. Now the problem with cross-validation, or the feature of cross-validation, is that since we are minimizing squared prediction errors or a similar prediction loss function, it focuses on prediction performance. So that means that it will, on average, tend to select too many variables. Because from a prediction point of view, it does not matter if we have some betas actually, which are close to 0. Right? So including some irrelevant variables, we'll just get coefficients which are close to 0. They will not change your prediction. On the other hand, leaving out relevant variables, that will definitely have a big effect. So cross-validation tends to select quite a lot of variables, which in itself might not be a problem if you're really interested in prediction. But if you're using the lasso for a fairly strong variable selection, and suppose you are doing this, you try to find a replicating portfolio and you really want to keep the number of assets low, then probably cross-validation is not your best choice to select lambda. In addition, of course, we have the issue that, for instance, in time series models, cross-validation is shaky at least. It's theoretically not appropriate, and whether it works well in practice really depends. Although, of course, there you could do, as I explained in the lecture on variable selection, you could do a time series alternative where you only do essentially one-way rolling or recursive window prediction. Now, an alternative that you might want to consider, particularly if you're interested in variable selection, is to use information criteria. And the information criteria are working exactly the same as before. Right? So we have the logarithm of the residual sum of squares. We have a penalty term that penalizes complexity. Now there's something subtle here, and it's something that I sort of skipped over before when I discussed variable selection, because then I directly said you have your penalty, which is depending on whether it's AIC or BIC, could be 2 or log n, and you multiply that by the number of variables that are included. And that was the case for the standard case. But actually what we have is the degrees of freedom of your model. Now, if you just look at the standard case where you compare all models putting variable in or out, the degrees of freedom is equal to the number of variables. So which is why I could say that. Now here it's not so trivial anymore whether this is still the case. Although in fact, people have shown, but only for p smaller than n, that the number of non-zero coefficients, so the L0 norm of your beta, is actually a unbiased estimator of the degrees of freedom. So in practice, you can replace this unknown quantity, degrees of freedom, with the number of non-zero coefficients. So what we simply do is we again have a grid of lambdas, evaluate this for a grid, and take the lambda which gives you the lowest number. Now I mentioned here p smaller than n. You can, of course, you could use it in principle for p larger than n, but you might see very strange results if you do that. It has a tendency to break down for too large p. Now we can find further details in the books if you want to have a look at how this selection is working. Now in GLMNet, for instance, the standard package in R, there this cross-validation is implemented. So if you want to, for instance, you have time series models, you don't want this, or you want to do an information criterion, then you'll have to move away from the standard settings in the package. Of course, there are also some packages which already did that for you. I will discuss them at a later stage when I will discuss an empirical application of the Lasso. For now, this ends this lecture on the Lasso. In the next video, I will go into extensions and modifications of the Lasso, because, well, we actually don't have to stick specifically to the form of the Lasso to still enjoy all the benefits of it. But that will be the subject of the next video.